Hello everybody and welcome to Unit 1, Section 3. It's going to cover Earth and how Earth fits into the larger solar system. So we're going to start with something called Nebula Theory. And the idea here is that originally there was this dispersed cloud of gas and dust, something which, might just look like a lot of empty space with these little particles spread out through it. And that over time, these particles are attracted to each other because of gravity, and they come in on each other, get denser and denser. And as they move together, they don't just all come in at once and hit a point. Instead, they come in together and flatten out into this rotating disk of material spinning faster and faster and faster, and getting extremely dense at the center. Date of this, kind of a funny date here, about 4.56 billion years ago. So, the center of this nebula gets so hot and dense that the individual atoms in it start to fuse together. You put two hydrogens together to form helium and so on. This is actually the exact process that happens in a nuclear bomb. It releases a tremendous amount of energy, but it only happens whenever you have an incredible amount of force pushing these things together. And this theory, Nebula Theory, is our basis for why the inner planets might be rocky and why the outer planets are made of more ice and gas. So if this Nebula Theory is true, we would expect all the dense material to be closer in to the center of our disk, and the lighter material to be further away. If this is true, then that would be the case. So this diagram here does a pretty good job of putting all that into view here. We start off with our dispersed cloud of hydrogen. It begins to contract due to gravity. Second stage here is as it contracts, it starts to swirl in on itself. It spins faster and faster and faster. The material in the middle starts to form a bulge, and everything else turns into a flat disk. The center gets so hot that we overcome a certain threshold and we begin the process of fusion. So the sun turns on, huge ignition, blowing away everything that was near it and starting the sun. And finally, our last step here is we have the process of accretion. So the material that's spinning around the disk. Well, it's not just spinning around playing nice. All that material is going to be bumping into one another. And the large chunk is essentially going to hit a smaller chunk, and they're going to form something larger, which is going to eat all the particles around that, and so on and so forth until we have all these discrete chunks swirling around the center sun, and that's the planets. And just to touch on this a little bit, what does the present have to do with it? So our principle of uniformitarianism, well, it turns out that using very, very powerful telescopes, we can actually observe this nebular solar system process going on far away in other star systems. So part of the reason why we have such a good idea about how our solar system might have formed is because we can look at this process happening right now in other places and say, okay, well, we're made out of the same stuff as them, we're a solar system. It makes sense that we would start with an idea that we have formed the same way. Just to give some of the terms here, this process whereby the little chunks hit each other and collide and form bigger chunks, which start to eat all of the smaller chunks around it and coalesce into these bigger spherical planetoids. This is called accretion. It's the process of accumulating material here. So as the outer portions of the nebula cool into this disk, the center, remember, is where the sun is, so we have the cooler outer portion. There are these random collisions, essentially. They cause the material to clump up and grow larger and larger and larger, and through gravity take in all the little loose debris around it. The result of this, again, if this theory is true, we would expect planets which are round, which they are, I believe, and isolated from one another, not super close, which again we find to be true. There's also a matter of, well, some of the debris swirling around the sun was never drawn in by a planet. You can imagine asteroid. This is our asteroid belt. This is a material which, for whatever reason, never came together into a planet the way that the other material had. And, we'll do more on this later, you would expect then that these asteroids are really, really nice for telling us what the original material was that the planets might have been made out of, whatever the primordial solar system material was. So Earth is, as you may know, one of 8, yes, 8 planets in orbit around the Sun. Sorry, not sorry when it comes to Pluto. And there's also about 140 satellites. These are moons or orbiters, asteroids, comets, meteoroids, dwarf planets, all the different little debris in the solar system which are rotating around the Sun. And we'll take a moment here, just between you and yourself, try to name the planets in order, if you can remember them, from the Sun outward. So, hopefully you might have come up with something that is a little bit like this. Terrestrial planets, the rocky ones in the inner, Mercury, Venus, Earth, and Mars. Moving outward, we have, well, first our asteroid belt and Ceres in it, which is a very interesting little planetoid, something we'll cover later. To the gas giants, call them the Jovian planets, sort of an older term for it. Jupiter, Saturn, Uranus, Neptune, and finally, well, unfortunately, Pluto is not a planet, but you work with old material sometimes, you might see it on there. Why are the inner planets rocky? So, touched on this a little bit earlier. If you want, go ahead and pause and see if you can recall what was covered a minute or so ago in the lecture. Why are the inner planets rocky? What does rocky even mean here? So, first thing is because of the temperature. The high temperature of the inner solar system means that the light stuff, especially your hydrogen and helium, your escape artists, essentially, would have been so hot that they could not stick to these planets. Instead, the planets are so hot, the gases are so hot that the gravity of the planets themselves is not enough to contain them. You can think of well, the fact that a balloon made of helium is not going to be bound by Earth's gravity. It is going to float off of Earth. So when it comes to the question of what happened to the original helium, we have a pretty good idea. Only the heavier stuff was left behind, constrained by Earth's gravity. Thing number 2, we talked about earlier, when the sun switched on, this would have released a tremendous amount of energy. Talk about the initiation of nuclear fusion in the proto-sun. This would have blown away the thick atmospheres of any of the inner planets. So this probably would have done a good job of wiping out whatever atmospheres the earlier planets might have had. And finally, gravity itself. So the densest part of our spinning nebula disk is going to be at the center. And we imagine that the not as dense material is going to be next to it. And as we move further and further and further and further out, we're going to get the lighter and lighter material. The heavy chunks are more affected by the gravity of what's happening in the center, so it only makes sense that the heavier chunks would be closer to it now. I have some video links here if you want a refresher or if you want a different formula material presented here. Stay tuned for section 4. We're going to be covering Earth's interior.